Welcome to the lesson on section 9.1, arc length. In this lesson, you'll learn how to use a definite integral to calculate the length of a curve given its equation. Before we use the formula, let's look at where it comes from. Shown below is a continuous and differentiable sample curve with points P1 and P2. Change in y and change in x between P1 and P2 are also shown. By the distance formula, the length of the segment from P1 to P2 is the square root of delta x squared plus delta y squared. By the mean value theorem, there exists a c on the interval from P1 to P2 such that the slope of the tangent line at c is equal to the slope of the secant line from P1 to P2. Solving for delta y in this equation, I find that delta y equals f prime of c delta x. Substitute this new expression for delta y in our expression for the length of the segment from P1 to P2 and factor delta x squared out of the radical. The integral of this expression calculates the sum of an infinite number of such segments along the curve, thus approximating the length of the curve. So the length of a continuous curve from x equals a to x equals b can be found by the integral from a to b of the square root of 1 plus f prime of x squared, where f of x is the equation describing the curve and dx is the infinitely small length of the segments we imagine breaking the curve into. Notice that the derivative of f must be continuous in order for this integral to exist. Here are a few variations on the arc length formula. Here's the one you've already seen, integrating in terms of x. On occasion, we may need to find the length of a curve that's given in terms of y. In this case, our limits of integration, shown as c and d here, would be y values, and the derivative inside the formula would be dx dy instead of dy dx. You may also be asked to find the arc length function of a given curve. By convention, the letter s is often used to represent arc length. So our arc length function will be called s of x. In case you were wondering, I read somewhere that the letter s is used because arc length is a specific type of distance, and s was the first letter in distance that wasn't already being used to represent something else. So anyway, to make the result of a function of x, let x be the upper limit of integration, and use a letter other than x in the integrand. The result will be a formula for the length of the curve as measured from point A to any point x on the curve. Let's look at how to find the length of the curve with the equation y equals the square root of 4 minus x squared from x equals -2 to x equals 2. In order to use our arc length formula, I need to find dy dx. So by the chain rule, dy dx is equal to negative x over the square root of 4 minus x squared. I'll plug that into the arc length formula and simplify. Using a common denominator to combine the 1 and the fraction, I get 4 over 4 minus x squared. And this simplifies to 2 over the square root of 4 minus x squared. Going on, I can integrate this using a trig substitution with x equal to 2 sine theta and dx equal to 2 cosine theta d theta. The limits of integration convert to negative pi over 2 and pi over 2. Substituting gives the integral from negative pi over 2 to pi over 2 of 2 times 2 cosine theta d theta over 2 cosine theta, which simplifies to 2. And this evaluates to 2 pi. Thinking about this graphically, y equals the square root of 4 minus x squared describes a half circle centered at the origin with radius 2. Half of the circumference of a circle with radius 2 equals 1/2 times pi times 2 times the radius, which is 2. And this equals 2 pi. So we got the same answer. This concludes the lesson on section 9.1 on arc length.